Hello, welcome to my lecture on object detection. Just a short video that will go over the basics of how object detection works and what it is as a discipline. So let's dive in. So starting off, object detection is a fundamental aspect of computer vision enabling machines to perceive and understand the visual world. So similar to how our eyes help us understand the world around us, object detection will help us isolate pieces of or help a machine isolate pieces of its environment, and the machine will thus in turn provide us intelligence. That's typically how the entire object detection discipline evolved. We will cover how object detection works, the techniques used, key applications, challenges, and future trends. It's a rapidly evolving field. There's been many technologies which have advanced the field of machine learning and object detection and visual recognition, and we'll talk about a few of those. Object detection is crucial for understanding. Object detection as it's increasingly integrated into its daily life. From smartphones to cars, cameras all around us. They are doing things like face detection, face motion detection, pose estimation. There's all kinds of things that object detection is used for in the modern day, and we want to see if we can break it down a little bit, but it is a vast discipline because there's many cases to consider. Image data is actually very complicated. Okay, so more formally, what is object detection? It identifies and locates. It's a process which identifies and locates objects within images and videos. So here's an example of an object detection framework. There's one of many, and it's detecting various objects very quickly. This is TensorFlow here, and as you can see, it's doing region segmentation of these objects: people, horses, food, and it's specifying what label is associated with these objects. You can detect multiple objects and their locations within a video. So see, as you can tell, like there's some kind of percentage of confidence that the object is what it is saying is being reported, and also the bounding box around each object tells you where the location is, and all this information can be extracted from this process as data, as numerical data, and analysis can be done on that. So unlike image classification, object detection finds and labels objects. So if you've seen image classification before, pure image classification, it's something taking an image and determining if the image looks like a cat or dog. This determines what's in the image, where it's located, and what the outlines of the objects that are in the image. So it's a more expanded technique with more advanced capabilities required in order to facilitate it. Compared to image classification. And many AI-driven applications use some form of object detection. GPT is an example of one of them. So if you're using GPT Vision, there's an object detection framework or a model that's built in to GPT to do that. And we could get into that at some point, but this is just focused on the basics of object detection. So this is an example of object detection pipeline. So what we have here is we have some kind of input data set, right? And so it looks like cars, and it looks like the silhouettes of cars. And there's some pre-processing stage which occurs, which probably changes and normalizes contrasts, aligns images a little bit, gets rid of excess noise, typically as pre-processing does with images. And it's fed through, these images are essentially fed through an object detection model, which and also an object tracking model, which kind of follows where the objects are traveling in this image, and that gives information like vector of direction of traversal and other pieces of like tracking information that are important. And over time, what this is doing is there's a performance evaluation to see how good the process is and how good this object detection framework is. And of course, sometimes what has happened, that performance data is fed into a model which actually learns how to optimize this object detection framework. So again, basics are images or videos are fed into a system. key patterns and features are identified. So if you're familiar with how convolutional neural networks works, and in this case, this is a DCNN. This is a specific type of convolutional neural network that's designed to detect these patterns. That is how object detection works from bottom up, the ability to find the nuanced features space of an image. Objects are classified into categories. So, for example, things like vehicles, things like food, things like, as I went into the previous slide, people. So all of these categories and category labels are determined. And the bounding box, which is the outline of the object, indicates what its position is. So there's some traditional techniques that are associated with object detection. One of those is called the sliding window technique, which involves dividing an image into smaller sections and scanning each one individually to detect objects. So this is kind of like what you can think of as like a brute force technique. So if you have some sort of fixed or variable size sliding window, it'll slide over the image, and it will do this iteratively as it slides, like say 1 or 10 pixels from left to right. It will run a convolutional filter, SCNN, on it and be like, okay, well, these images are in this block, and then move to the next block, and so on and so forth. And you can imagine a technique like that being very inefficient, right? Because it has to slide through all of the windows one by one and do possibly thousands or millions of detections on a single image. And there's a lot of redundant information in there because the sliding window captures a lot of information from previous sliding windows. So we are potentially doing many repetitive object detections in those windows. Another technique is called selective search, which is a more efficient technique which generates region proposals by identifying areas within an image that are likely to contain an object. And so the region proposals are chosen in different ways. There's actually, we're not going to go into region proposal networks, RPNs, but in this section, or in this particular demo, but note that there is a way that regions of images can be intelligently segmented out for containing objects, and a lot of that has to do with pixel density and superpixels, and the way that regions are constructed based on changes in intensity. So kind of like people were doing filters back in the day to determine where changes in intensity occurred in order to create boundaries in objects. Similarly speaking, region detection networks are doing that after some sort of segmentation process which combines regions. The traditional methods like these are still slow. Like it takes a long time to come up with optimal regions due to the iteration and the image detection that has to occur. If you think about the way that selective search can occur in videos, the base selective search would be inefficient because you're redoing between each frame a lot of region computation. So you can think that there's more efficient ways of doing this where you retain some of the region information from frame to frame, so you don't have to repeat the selective search algorithm over and over again. Modern object detection relies on advanced learning techniques such as CNNs. So again, you could have done, you could use old school techniques. Even CNNs these days, the older basic networks have been improved upon significantly from 2012 to 2014 and 2015 and so on, when the original models came out, but which we'll talk about. And this to the right is an example of the segmentation generation of regions which combine, and as you can see in this image to the left, this woman in this television set, or painting here rather, is eventually this outline of them is approximately determined through this segmentation, and thus the bounding box of each can be picked out after the initial thousands of bounding boxes. So modern techniques such as those in the RCNN, the region CNN family, combine to the generation of region proposals with CNNs. Okay, so if you get the region proposals, which can come from different techniques based on CNNs finding intensity maps, the region CNN then can actually detect objects using a convolutional neural network in particular regions to determine, what particular objects lay within those regions. And regions again can be defined in different ways, whether it's tightly bound around a specific object or whether it's not. So the YOLO model was a powerful model. Let's go back a little bit. That revolutionized object detection because it did so in a single pass, meaning it could just run against a single object detection model, without having to do like multiple stages of like region generation and then detection from those regions. It could just simply be like, oh, there's something within a particular box, and it'll do it much faster. We won't go into the details of how YOLO works, but the papers are online and they're quite interesting. There's the single shot detector model offers a balanced approach to object detection because, and when we talk about balanced approach, because again, object detection can be slow and object detection can be fast. And typically you want faster object detection for a real-time network, right? If you have like real-time video of like a video feed, then an object detection network that is single shot would be more appropriate, and YOLO can do this, for example. This of the different versions of YOLO, but it's not. It might not be as accurate or nuanced in what it's retaining, because it's not actually doing a lot more complex processing in order to obtain more intelligence, like something like a more advanced RCNN multi-stage feature pyramid network-based model with the backbone has. Again, not going into too many of the details, but example is Facebook's Detectron, which would do multi-pass model detection. And then it would help you segment much more effectively than something like YOLO. At this point in time, things change. And I just talked about the speed and accuracy between both. And so just a quick visualization on the right. Here is kind of like how YOLO works. So YOLO will create bounding boxes around images, which it uses several of those techniques we discussed to do so. And then it has this class probability map, so it can determine which class each of the regions belong in based on the objects and regions detected, and then it can do a final detection based on a bounding box of that object. So pretty straightforward, but it's very fast compared to other systems, and that's why it's used in many cases. So key applications. We want to identify pedestrians, vehicles, obstacles. We detect suspicious activities and objects, right? So, for example, in a security system or intrusion detection system, we want to see potential intruders, and so we want to detect, and this is actually done in industry with security cameras. They have object detection models built into the camera. And of course, another advancement is in medical imaging analysis to determine if something is potentially malignant or benign, for example, a growth, if there's some issue with a particular tissue. That rhymes, that can be detected. And as of recently, I believe some new model came out that could detect cells on the microcellular level and determine if there's cancerous property within cells that are 1,000th of the size of a human hair. So this technology advances quite fast. And again, it can enhance customer experiences through smart systems because, for example, it makes things like checkout, like fast checkout possible, where it can detect objects as you pass them through a fast checkout line. And as you can see in the right, there's this image of these. This is 3D object detection. So the examples I showed you before were a 2D, where you see a bounding box on a 2D image. But this is an example of on a 3D image. And these are essentially creating bounding cubes on objects. And you can imagine that there are frameworks. Meta is actually getting powerful at doing this, but you can imagine that there are frameworks. There are complexities, and we'll talk about in the next slide some of the complexities with object detection, and it would apply to the 3D cube detection much more because the dimensionality has increased. So we're just going to briefly talk about challenges in object detection. The trade-off between speed and precision, which is something that YOLO versus Detectron, for instance, would be doing. The YOLO model would be detecting objects very fast, but then the precision could be much slower. So it might be able to find something, but it might not be able to accurately detect what it is as fast as something like a RCNN Detectron multi-pass network. Different difficulty with different lighting, angles, and occlusions. This is like one of the quintessential problems with object detection models. How much will an object detection model be able to determine of what an image of something is or what an object is if it doesn't have more information about it? Well, in those cases, there's predictive methods to determine what could be the rest of the object. Actually, that's part of like what AI is doing, right? It's doing predictions, but the predictive capabilities have to increase even higher. Lighting is very problematic, so there's techniques to enhance lighting on objects, things like something called dark channel prior, which will essentially illuminate certain regions based on what's called the probability of the dark channel. I'll go into that in another example. And obviously, angles on objects increase the complexity, and that's been issue for a long time. Especially like a canonical example is with cats. When you change in older models the orientation of a cat, sometimes the older models weren't able to tell it was a cat. So some objects are underrepresented in data sets. So for example, you can have a lot of unknowns, which is actually a big problem in things like complex investigation of scenes that are not local, but of objects that are like foreign. So for example, if you go to like, if your model doesn't have a sufficient number of like objects that are maybe like Egyptian artifacts that are excavated from a tomb, it might not be able to detect and understand what all of these are, even though it might be able to understand like generally that this might be a vase, or a vase or something else. So essentially, you need to increase the representation of the data set for the intended application. And again, they demand significant processing power. These are doing image detection. Images are 2D data, and in the case of 3D data, you could do 3D object detection, so that's much more. The curse of dimensionality comes into play, and thus that means you have much more processing you need to do. So here's some future trends. So we're and the future is now. Actually, the vision transformer is being used, but CNNs were typically used for object detection, and as the transformer model became quite powerful for text-based learning, they found ways to make the transformer model powerful for vision-based approaches. Moving detection to edge devices for real-time use, and that's a really amazing thing because these models can be run on the cloud, which you have cloud processing, but what if you want to run the model on your mobile? And you can do that with edge devices essentially these days, but it becomes even more powerful when edge devices, basically things like your edge server or your mobile device and on the edge of the network essentially, and you can use that in isolation without having to use a remote model. They will just keep getting faster. They will be able to use more dimensions. You can see things you can see there's different, more advanced methods of image segmentation where you can now segment entire bodies. Meta again has been making a lot of progress in this area, but you can create essentially 3D characters from the use of motion generation from people, human beings in a scene. So this is again advancing, and it's extremely fast and much faster than it used to be to do these with more advanced models and the data that's being obtained about people and objects and environments. And of course, we have to address privacy and bias concerns because anytime you're doing object detection, detecting something, you could use it for something like a red light camera, right? And in this case, a red light camera would be there's in different states, there's different uses of the red light camera to identify things like license plates on whether there's a privacy concern there. If somebody was speeding or whatnot, then identifying that person could also be an issue if it's done through an AI model. So again, there's many privacy concerns even beyond the world of text here. Okay, so that's pretty much my presentation. If you have any questions or if you want to subscribe, please comment below. And yeah, otherwise, have a good night, and I will be back with another video on the object detection and possibly a part 2. Thank you.